we get into says what information do you need to write an equation that represents an exponential function? And remember, this is the general form for an exponential function. And these letters mean something. A is your starting point. If you're given like a scenario. In a graph, the A value is your y-intercept. Okay? What's your B? Everyone should know this answer. What does the B stand for? It's the growth factor. Your B is your growth factor. So again, if something's being doubled, tripled, and so on. Okay? And then of course, Y is what you're solving for, your dependent variable, and X is your independent variable. Okay? So that's what those mean. So here's our scenario. Let me scroll this down here a little bit. So it says Ghost Lake is a popular site for fishermen, campers, and boaters. In recent years, a certain water plant has been growing on the lake at an alarming rate. The surface area of Ghost Lake is 25 million square feet. So this is how big the lake is. Okay. At present, the plant covers 1,000 square feet of the lake. The Department of Natural Resources estimates that the area covered by the water plant is doubling every month. So, again, this is a general form, right? So, what's our A? What's our starting point? What would you say our A value is here? Someone raise their hand and tell me. What are we starting with here in this scenario? Nobody? We're starting with 25 million square feet? 1,000, because that's 25 million is how big the lake is. So our A is 1,000, right? And again, right here, at present, the plant covers 1,000 square feet of the lake. Okay. What's our B? What's our growth factor? Anyone know? What does it say there? Reese? 2, right here. It says doubling every month, doubling. So our growth factor is 2. So your equation should be that. Don't forget the y equals. If we don't have y equals, it becomes an expression, not an equation. All right, so let's kind of talk about what each thing means here. So if we solve for y, what are we talking about? So if I plug in, I don't know, a number for x, and we figure out y is a certain number, what are we actually finding out? What is y? No, y is not 25 million square feet. When we solve for y, what are we finding out? Yeah, the area covered by the plant, right? So this is the area covered by the plant. And remember, the area is in square feet, so we're talking about the square footage here. Okay? Now we already talked about the 1,000. What's the 1,000 represent again? That's kind of our starting point, right? At present, the plant covers 1,000 square feet of the lake. All right? And 2 was our growth factor. Okay? What does X represent here? What do we plug in to find out how much area of the lake is covered? What do we have to plug in? What's X? Anyone have an idea what X could be in the scenario? Anyone have an idea? What's X? What do we plug in, Reese? Months. Right, X is months. That's your time. Good. X is months. Is that for Mr. Cicchini? Thank you. Okay. So, it says compare the equation to the equation in investigation 1. Well, okay, so here's what we're dealing with now. And I'll give you like a little refresher course. Just sit on the desk. This is what we kind of dealt with in investigation 1. We saw 3 different types of equations pretty much, right? Remember these? Right? It was the king's plan, then we had the queen's plan, and we had the king's second plan and new plan. And how does this equation compare in terms of similarity-wise to what we see right here? How do these equations kind of compare in a similar way? How are they similar? Okay, they both have y equals at the beginning, right? I agree with that. What else? Well, this one doesn't have x minus 1. How are we comparing this to this one? What's in front of the x minus 1? What's in front of the x minus 1s? Not a variable. The growth factors. They all have the growth factors, right? And these two had the same growth factor, right? Besides the exponents being x minus 1 in investigation 1 and this one being x, what's different about the two equations? What do you notice that's different about the two? Connor? Oh, yeah, they had this part here, right? We didn't have that in the first one, did we? Actually, we did, but we didn't write it. Because what did we start with, right? In investigation 1, what was the first square? How many rubles were on it? So we actually started with 1, right? So technically, we could have wrote it like this. Here's the thing. This is why we didn't. Does 1, when you found this answer, right? Does multiplying by 1 change any of the numbers? No, it doesn't. So that's kind of like the same reason why we don't write 1x. Instead, we just write x. Because the 1 doesn't change anything. So we usually only write the a value in when it's bigger than 1. Okay? Because it's not going to change the outcome of y. Does that make sense? So that's, yeah, you're right. So technically there was the a value there. We just never wrote it because it was 1. And it, like I said, it didn't change anything. All right? So let's fire up this calculator here because I want to show you how we can put this into the calculator and show how easy it is that you can make a graph out of it. And I've been misplacing my calculator all day. Uh-oh. Oh, is this one not working? Well, that one works. Oh, I know why that's up there. Oh, there it is. It's hiding on my document camera. Okay, so if I go into my y equals and I type in 1,000 times 2 to the x power, okay? By putting that in, I now have my equation in the calculator. Don't forget, once I put it in, I have to hit enter. So once I type it in and I hit enter, it's entered in the calculator. Now that I have my equation in there, now again, yours will look a little different, right? Yours will have 2, have the arrow in an x, right? And that's okay. As long as the arrow's there, that means you got the exponent. So, but now that you have that in there, you can do lots of things with it. Like number 1, you can check the table by hitting the second function, graph. And let's just scroll up here a little bit to where we started 0. Okay, so I got all my points right there. So for example, like when I got to do a graph, I had the points right handy to me right here in my calculator. So again, let that help you when you're doing this. So if I go to my graph, which I filled out here, so there's our area covered, right? In square feet, there's our number of months. So at 0, if x was 0, what does it say in your graph what y is on your table? If x is 0, what's y? 1,000, right? Because 2 to the 0 power is? What's anything to the 0 power? 1. And 1,000 times 1 is 1,000. So there's the first point right there. And then at 1, if we plug in a 1, that's 2,000. It's doubling, right? Then it goes to 4,000. and then 8,000, and then 16. I know the other one's kind of off the chart, but we got enough on here to show our curve. Okay. We got enough on there to show our curve that it's not a straight line, it's exponential, and it's increasing at a high rate. Okay. And again, the next question I believe asks us, compare the graphs of the exponential functions in investigation 1. Well, in investigation 1, weren't they all curves also? Yeah. Not the same numbers, but they were the same shapes, right? And exponential graphs, for the most part, except for the numbers, are the same shape. Just like linear lines are straight. These are curves. They start off kind of slow and shoot right up. That's just how it works. So again, the calculator can really be your friend in this investigation because you're dealing with big numbers here. Exponential functions, you're going to deal with big numbers because you're multiplying. Where in linear, we've added most of the time, right? We've had that constant rate of change. All right. 3 is what I want to talk about. Because it talks about, so let's recall that for each independent variable, remember we refer to x as the independent variable, right? There's exactly one value for the dependent variable. We refer to the dependent variable as y. So is the plant growth relationship a function? And meaning this, and again, for the definition of a function, okay, for every y value, there is only one x value. That means they don't share points. Okay? That means two x values don't have the same y value. That's what that means. Okay? That's what makes things a function. Okay? They've also referred to, you also might have seen this as also what they refer to as a function. This is called function notation. You've seen that before? F of x? That's a fancy way to write y, basically. Okay? So in a table, we can find out things are a function if I have a bunch of numbers here, right? Oh, this should be 15. So you notice how every y value only has one x value. They don't share any values. Like, for example, 7 doesn't appear in 0 and 1. That would be sharing an x value. Okay? So just by looking at the table, that's how you could tell this would be a function. Because they only share this. There's one x value for every one y value. Nothing is shared. Okay? In a graph, we do something called the vertical line test. So let me go back to the graph. Right? You're probably wondering, why does he have a blue line there? Well, if I take this line and drag it through our graph, this should only touch the line every time at one point. Right? It doesn't cross it twice. Like this curve doesn't go back up and then weave through and come back, right? So as I pull this line through, it only touches at one point. So we can use the vertical line test on graphs to find out if functions are a point. That's why linear lines are functions also. Because a linear line just goes straight, right? There's no bend. So if I drag a straight line across another straight line, it's only going to touch it one time, right? Unless the line is vertical. Right? Then when my line hits that line, it touches not at just one point, it touches at every point. And those are the only graphs that aren't functions, are like x equals 6 or x equals -2. Vertical line graphs. Okay? All right. So now let's get back into what we're supposed to do here. Answer questions on this, what we figured out. So how much of the lake surface will be covered at the end of the year by the plant? Well, x was what? I think Reese said it, right? What was our x variable supposed to be? Months, right? So what are we going to plug into x if we need to find out how much area is covered at 1 year? 12, because there's 12 months in a year. So if you take your equation, y equals 1,000 times 2, and we have to put that to the 12th power, right? What do you get? Plug 12 in for x, and you should solve it. Did you get that? Because you have to plug in a 12 for x. So 2 to the 12th power, and then you multiply it by 1,000. Well, 2 to the 12th power is 4,096. And when you multiply it by 1,000, that makes it 4,096,000. And notice the notation at the end. We're talking about area covered, right? Square feet, because we're dealing with area. That's important. Okay? All right, the last thing that we're going to do, and I'm going to give you guys a few minutes to figure this out, okay, is how many months will it take for the plant to completely cover the surface of the lake? Well, remember, how big is the lake again? How big is the lake? 25 million square feet, right? So if I go back up to my table, right, we don't see 25 million in any of these y values, right? So if I go down, it's not till 10 does it start showing scientific notation, right? Which means that's 1,200,000 or 1,020,000. 1,020,000. So you know it's got to be more than 10 months. So what I want you guys to do, where I'm going to pause the video, is I want to see where you can come up with where it's at, where it's going to pass 25 million or hit 25 million. Okay, I'm going to give you a hint. It's not exact. Okay, so just be ready to explain that. All right, so we're going to pause and give you a few minutes to go ahead and solve that. What'd you guys come up with? What'd you find out? Someone said 14 months? Someone said 15? Both? How can it be both? Can't be both. You're close. Both answers aren't right, actually. It's not 13 and a half. It's not 16. Now we're just making up numbers. All right. When you put in 2 to the 14th power and multiply by 1,000, you get 16,384,000. And then when you do 15, you get 32,768,000. Well, 25 million square feet is between those two, right? So that means it's between the 14th and 15th month. So if you think of, let's say a month is 30 days, which is it closer to? Which number is 25 million more closer to? The top one or the bottom one? Which number, 16,384 or 32,760, is 25 million closer to? It's closer to the bottom, this number. This is only about 7.5 million away. This is over a little almost 9. Okay? So it would mean it would probably be half that past the halfway point of the 14th month. I think it's like 14.6 something. So it's past the halfway point. So if you were counting 30 days in a month, probably that like 17th, 18th, 19th day-ish, somewhere in there, if you want to get exact. But yeah, no, it's between the 14th and 15th month, closer to the 15th than the 14th. All right, it's past that halfway point. All right? So that's how we use exponential functions. So I'm going to stop the video.